Welcome back, Sayo. How was your summer vacation?
It was great. Me and Alba had a lot of fun there. We even went parasailing. So, what's today's problem?
Well, actually, there's something I want to show you first. Come with me. We've reached the end of the month, and we're greeted with this door.
Do you think the end of each month will feature a very hard challenge?
Probably not. We've just proved the Pythagorean theorem 34 times. Oh look, there's a problem coming up. To open this door and move to the next level, find the volume of these three shapes.
Well, the next section will be calculus, right? I don't see why we can't use that in the... Oh, come on! What do you mean we can't solve integrals?
Come on, it doesn't say that. It just says we can't use anything above an 8th grade level. Besides, the proof of a circle uses a precursor to calculus, so we can just use that.
Okay, so we got to solve these volumes in this primitive way, I guess.
Sure. Let's begin now. First up is the easiest. We need to find the volume of this torus.
I'm sure you have a lot of memories trying to find the volume of that one.
Shut up. This proof would not involve in finding the integral of sine squared x. Our proof today will be similar to the one I showed about the area of the circle.
That involves splitting up the torus into small chunks, and then rearranging chunks into a cylinder.
Twice the length of this cylinder is equal to the length of the outer circumference plus the length of the inner circumference, which is 2 pi capital R plus lowercase r plus 2 pi capital R minus lowercase r.
And that just cancels out to 2 pi capital R. The radius of the cylinder will be lowercase r, so the total volume of the cylinder is 2 pi capital R times pi lowercase r squared.
The same formula I figured out in the other video. Next up, what is the volume of the cap of a sphere? Of course, we could calculate it by taking a sector of this sphere and then subtracting the cone, but I want to take a different approach.
Different approach?
Of course, but first we need to derive the volume of the sphere. This is a cross-section of a sphere inside a cylinder. The triangle here is a cone. What we want to show is that the volume of the cylinder minus the volume of the sphere is the volume of the hemisphere. And we do this by examining a cross-section of the diagram. What's the area of this slice of the cylinder?
Well, of course, it's just pi r squared.
What about the cross-section of the cone?
Well, calling the height between the bottom and the cross-section h. Using similar triangles, we can see that the radius of the cross-section is also h, so it's pi h squared.
Now for the cross-section of the sphere, we have to use the Pythagorean theorem.
Just after we proved it 34 times.
Doing the math, you get that the area is pi times r squared minus h squared, which is just the cross-section of the cylinder minus the cross-section of the cone. Then it's easy to see that the volume of the cylinder minus the volume of the cone equals the volume of the hemisphere. A corollary of this is that the volume of a cylinder with height h and the volume of the cone with height h equals this part of the sphere. And then we can subtract that from the actual sphere and we get the cap.
You can also derive a formula that's based on just the radius of the base of the cap and its height. Now I'm feeling confident. Show me the last one. What is that?
The intersection of two cylinders, of course. The formal name for this is a bicylinder, but it's also called a mohair fungi in China. I got that wrong, didn't I?
Well, I don't speak Chinese either.
Let's do what we did for the sphere and just look at the cross-section. Assuming that the radius of the cylinder we cut it from is r and the height from the center to the cross-section is h, we get that the area of the cross-section is 4 times r squared minus h squared.
That sounds similar to the cross-section of the sphere.
I already said that.
Yeah, I know.
Well, anyways, do you want the easier proof that I just found about a few minutes ago, or the harder proof that was going to be the intention of this video?
How about both?
The easy proof is just like the one related to the area of the sphere, but this time instead of a cone, it's a pyramid. as you can see from the diagram here, the area of the cross-section of the pyramid is 4h squared. This results in this formula. Now anyways, onto the harder. Cut the bicylinder into thin slabs of tight delta h. The volume of a single slab is roughly 4 delta h r squared minus h squared, where h is the height from the center to the top of the slab, or the bottom distance from the bottom half. Summing up all the slabs, we get 2 times 4 delta h r squared plus 4 delta h r squared minus delta h squared plus 4 delta h r squared minus 4 delta h squared, all the way up to 4 delta h r squared minus r over delta h squared delta h squared. Given some calculators, this results in the sum of squares. And if you remember this special formula, this just simplifies into this, and we can multiply out delta h, letting delta h get closer to...
Hold up. This is just calculus. You said we didn't have to use that.
And we didn't in our first proof. Actually, all three proofs that I've shown is similar to calculus in a way, in the sense of adding up thinner and thinner chunks of the shape.
Even the first and third proof, we just compared areas.
And we assume that for all heights, if the areas of the cross-sections are the same, then the volume of the whole total shape are the same as well. This is called Cavaliere's principle, and it's an early step towards integral calculus.
Look, the door just opened.
Well, Sayo, do you want to go inside?
You know what? Let's do this.